Bismillahirrahmanirrahim. Assalamu alaikum. Last time we discussed Article 7.1, that was a review of some basic integrals, and I went through the proofs of someone, discussed some of them briefly. Today I had to go into Article 7.2, which is all about integration by parts, and there will be from very simple to very complicated problems that we'll be dealing. But before that, I want to share a basic important technique that is frequently used in solving problems as well as proving formulas. For example, this is a fundamental formula for power integral. When you have to integrate x power n, power is increased, and the increased power divides the term x power n plus 1, which is possible when n is not equal to -1. But if n is equal to -1, then you know that the integral is integral of 1 upon x is ln x. We discussed this briefly. This is the case of the same thing with n is equal to -1. Now, motivated with this fundamental rule that we call power integral, we have extension of these rules to rule number 3 and 4. Now, if you have some function whose power is n in the integrand, but along with this term, we have the derivative of the function inside. So we have the result exactly same as the 1, formula 1. And how can we prove 3 is a simple technique of substitution. In this, we substitute q is equal to fx, and that means du is equal to derivative of f into dx, and that makes the integral in place of fx u raised to power n. In place of f prime dx, you have got du. So you have effectively this form, and that makes it u power n plus 1 upon n plus 1 plus c, and hence this form. As far as 4 is concerned, we use exactly the same thing. And we see that numerator is f prime x dx, that is du, and denominator is u. So the result is u raised to power n plus 1. Oh, sorry, not this. Rather, it is the second form, and we get the result as ln of u plus c, and that gives you this formula. Now, in case of this formula, people very frequently remember this technique or formula. If whenever you have a situation for an integral where integrand has the form denominator में एक function है and its derivative is available in the numerator, so we can directly write down ln f. And if you absorb this idea, the same goes here. There is a function whole raised to power some integer or some number not equal to -1, and the derivative of this function inside is present in the integrand as a multiple. Then we can write down directly this. So this technique is frequently used. For example, uh, somewhere we have used integral of secant. Now, secant is not the derivative of any function. Cubic trigonometric function है fundamental. Sine, cosine, उनके जो डेरिवेटिव होते हैं, उन्हीं डेरिवेटिव को हम एंटी डेरिवेटिव कंसीडर करते हैं. यानी टेंजेंट का डेरिवेटिव सेकंड स्क्वायर है, तो सेकंड स्क्वायर का एंटी डेरिवेटिव टेंजेंट है. तो इस तरह secant itself is not the derivative of any function. So if we want to find an antiderivative or integral of secant, we use this technique. Basically this technique. We try to form or transform the integrand into a shape where we have some function in the denominator. In this case, we have secant x plus tangent x. So I have divided this by secant x plus tangent x. So I multiply the numerator with secant x and tangent x. So secant x multiplied by tangent x plus secant x. So that the integral in fact becomes what? Secant x into tangent x plus secant square x whole divided by secant x plus tangent x. And note that now we have a denominator whose derivative is exactly present in the numerator. Secant derivative, secant into tangent, tangent derivative, secant square. And that is this form, a function in the denominator, derivative in the numerator. So it goes into log of the function in the denominator. Plus c. So this kind of technique is very frequently used. And some of the problems that appear to be very complicated, for example, tangent inverse x upon 1 plus x squared. I have kept it relatively simple. And if I want to make it more complicated, I put tangent inverse raised to power 3. Now, the technique I'm discussing applies here. If you are not able to recognize how to apply the technique, the trick is to use the same process that you use to prove the formula. And that is, जिस फंक्शन की पावर है, tan इनवर्स की पावर है, तो उसको आपने वेरिएबल यू कर दिया. And I hope some of you know the derivative of tan inverse x, and that is 1 upon x square, 1 plus x square. And that makes du is equal to dx comes here, dx upon 1 plus x square, so that this integral becomes what? Tan inverse is u, so u raised to power 3. Dx upon 1 plus x square is du. So now it is simple matter of power integral. So u cube upon 3 plus c. And the final result is 1 upon 3 u again replaced by what I am doing? Power 3 है तो power increase करनी है. U raised to power 4 upon 4 1 upon 4 u raised to power 4. So what was u? It was tan inverse x raised to power 4 plus c. So please remember this basic tool, which is very frequently used at least in the proofs of many of the integrals that we considered last time. One more thing before I go to start 7.2. मैंने इनमें से कुछ प्रूफ करके दिखाए थे आपको, और नए फंक्शंस साइन हाइपरबोलिक और कोसाइन हाइपरबोलिक इंट्रोड्यूस किए थे हमने, और मैंने इसमें ये वाला जो इंटीग्रल है इसको प्रूफ करके दिखाया था, and we found out that this formula is not written correctly. It is x square minus a square, so here it should be x square minus x e square. उसको मैंने आपको प्रूफ करके दिखाया था using hyperbolic function. So I am sharing one of these formulas proofs without using new functions, instead of using trigonometric functions. ये मैंने करके रखा हुआ था dx upon x times square root of x square plus a square. So let us see where it appears here, number 27. Before I describe this proof, let me tell you that amongst the general techniques, substitutions, when you have got under the root, say x square minus a square, under the root a square minus x square, under the root a square plus x square. जब इस तरह की expressions होते हैं हमारे integrals पे, then what kind of substitutions are generally used? X square minus a square के case में we use substitution a secant theta. In case of a square minus x square, you can use x is equal to a sin theta or a cos theta. And finally, in this form, a square plus x square, you can use substitution a tangent theta. Now, this is these substitutions are motivated by trigonometric formulas. For example, this is motivated by 1 plus tangent square theta is equal to secant square theta. So if you have got tangent square, it will be secant square minus 1. So secant square minus 1 बनाने के लिए ये substitution. And a square plus x square में a tangent theta रखने का मतलब है कि you are trying to construct what? A square plus a square tangent square, that is 1 plus tangent square. So this will simplify to secant theta. This will simplify to tangent theta, or basic trigonometric identity sin square theta plus cos square theta is equal to 1. So cos square theta is equal to 1 minus sin square, or sin square theta is equal to 1 minus cos square. तो इनमें से कोई भी substitution करके आप वो form बना सकते. So let me come back and as I indicated, जो list थी बेसिक इंटीग्रल्स की, उनमें से 27 नंबर जो है उसमें एक्स स्क्वायर प्लस ए स्क्वायर है. मैंने जो लास्ट टाइम एक इस तरह का प्रॉब्लम फॉर्मूला प्रूफ करवाया था, उसमें मैंने हाइपरबोलिक फंक्शन इस्तेमाल किया था. दैट वाज जस्ट बिकॉज मेरी उस डिस्कशन का एक पर्पस ये था कि आप लोगों को मैं हाइपरबोलिक फंक्शन से इंट्रोड्यूस कराऊँ. Of course, that was not by any mean a complete introduction. As and when we will require, we will consider more of hyperbolic. But here, a usual method of proof for integrals of this type, number 27. इसमें अभी हमने बात की कि x is equal to a tangent theta substitute करेंगे, जिसकी वजह से dx will take the form a secant square theta d theta. So dx is replaced by a secant squared theta d theta. In the denominator, you've got x. So a tangent theta is outside, and x is equal to a squared tan squared theta under the root plus a squared. This a cancel out. We are left with secant theta. Secant squared theta in the numerator. Tangent theta outside the root. A square from under the root taken common is a. Under the root, what we are left with is 1 plus tangent square, which is secant square, and under the root होने की वजह से वो secant हो गया. So 1 secant power is cancelled from the numerator. So what we are left with is 1 upon a secant upon tangent. In place of secant, let us write 1 upon cos theta. In place of tangent, let us write cos theta upon sin theta. So, tangent की जगह पे denominator में sin theta upon cos theta होगा, जो ऊपर आके cos theta upon sin theta हो जाएगा. So cos theta cancel out, and we are left with this. 1 upon sin theta d theta. Integral cos theta d theta. We just discussed that the integral of cos secant theta is derived here. Similarly, you can derive integral of cosecant theta, cosecant x dx. So cosecant के case में we multiply and divide with the negative of cosecant plus cotangent, and that results into negative of ln of cosecant x plus cotangent x plus c. So using when we reach this form, integral cosecant theta, so we remind ourselves that this integral is minus ln cosecant theta plus cotangent theta, of course, plus c. So our integral that we are trying to solve is in what form now? Minus ln of cosecant theta plus cotangent theta plus c. Now this substitution we made in the beginning, original variable is x, our result of the integral is in the form of theta. So we have to go back to the original variable x. X is equal to a tangent theta can be written as tangent theta is equal to x upon a. That means cotangent theta can be written as a upon x. So here in place of cot theta, we can replace a upon x. We know that 1 plus cot square is equal to cosecant square. इसका मतलब है cosecant can be written as under the root 1 plus cot square theta, and cot theta is a upon x. So cot square theta will be replaced by a square upon x square. इसमें आप एलसीएम लेंगे तो न्यूमरेटर एक्स स्क्वायर प्लस ए स्क्वायर बन जाएगा, एंड एक्स स्क्वायर जो डिनोमिनेटर में है वो स्क्वायर रूट से बाहर आके सिंपली एक्स रहता है. So this was our result in terms of theta, cot theta in terms of x, and cosecant theta in terms of x. Substitute both these forms into the integral obtained, and we have this shape. In place of cosecant, we have got this. In place of cotangent, we have got this. Take the LCM, and we leave the result as it is. So this is the usual way of proving these kinds of all these kinds. कुछ के लिए मैंने आपको हिंट दिया था कि ये सब्स्टिट्यूट कर दीजिएगा, उसकी जनरलाइजेशन मैंने अभी आपको बता दी कि किस फॉर्म में क्या सब्स्टिट्यूट करना है. यस, हम इन सब्स्टिट्यूशंस की जगह जिसमें ट्रिग्नोमेट्रिक फंक्शन इस्तेमाल किए हैं हाइपरबोला भी कर सकते हैं, एंड वी स्टिल हैव द सेम रिजल्ट. बट जनरल प्रैक्टिस एलिमेंट्री लेवल पर लोग इस किस्म के एक्सप्रेशंस में ये ट्रिग्नोमेट्रिक सब्स्टिट्यूशंस इस्तेमाल करते हैं. With this discussion on some of the things related to the last lecture. Now I come to the next topic, integration by parts. Many of you hopefully remember this integration by parts, but still there may be some people either have no exposure to integration by parts, or they went through this, but they don't remember it, or they could not absorb it correctly. Now, when we have the heading integration by parts, we have an integral that involves product of two functions. In differentiation, we had the formula for the product, the derivative of the product of two functions. Here we have to develop a formula for the integral of the product of two functions. The integrand is now a product of two functions. First, I have noted as small f, a second f capital. To develop the formula for integration by parts, we consider another function, capital G, such that if I take the derivative of capital G, that results into small g. When derivative of capital G is small g, that means the integral of small g is capital. That means I can write down the derivative of the product of small f and capital G. Derivative of the product of small f and capital G. That means differentiation का u into v rule इस्तेमाल करूँगा. So first function as it is, derivative of second function v prime. Then uv rule इस्तेमाल कर रहा हूँ. First derivative of the first function and second function as it is. Then I remember that g prime is small g. So g prime की जगह small g रखी है. And f prime into capital G as it is. Now, if I take the integral of this line, this will be integral of this side and integral of this side. So ये जो integral है, उसको मैंने under the integral as it is लिखा है. तो कुछ भी नहीं किया. Here it is the derivative of product of two functions f and g. So when I consider integral of d by dx of product of two functions, what happens is that dx cancel, integral d both cancel, and we are left with only small f into capital. Integral is involved here. Now let us see what terms are associated with the integration process. एक term f into g है, that has to be integrated. एक term f prime into capital G है, which has to be integrated. And the other side we write for the time being as it is. Now this is what was our target. So target it is kept on one side. All terms taken to the other side. Now this term when taken to the other side will become negative. What happens to this term? Small f. Capital G was integral of small g. This term comes here. Integral of, this is an integral of product of two things. One is the derivative of f, small f. The other one is the integral of small g. And that becomes the formula for the integration by parts. This is sort of a proof of the formula for the integration by parts. And we have, in general, a trick or a pattern in our minds to remember that formula. First function as it is, integral of second function, minus integral of product of two things. The derivative of the first function into integral of second function. The product completes, and this product has to be integrated. यहाँ जो dx दो दफा आ रहा है, I hope you understand why it has appeared twice. एक while replacing capital G by integral gx dx, और एक दफा जो है वो इसलिए कि हम इंटीग्रेट कर रहे हैं इस प्रोडक्ट. तो टेक्निकली तो dx दो दफा आता है, लेकिन आमतौर पे हम ऐसा नहीं करते. f into g, we just write down f integral g prime dx minus f prime into g dx. बस ये लिख देते हैं. लेकिन असल चीज जो है वो, now there is an alternate method. Many of the students in their school days, if they study integration by parts, वो इस तरह से करते हैं. मैं इसको अगर कोई स्टूडेंट एग्जाम में करता है और सही तरह से कर देता है, I accept it, but I don't waste my time on this because मेरा आमतौर पर फोकस जो है वो बेसिक्स पे होता है. बेसिक ये है कि इंटीग्रेशन बाय पार्ट का ये फॉर्मूला प्रूफ करना. इसको भी हम प्रूफ कर सकते हैं, बट जब हमने कर लिया प्रूफ काफ़ी है. एंड इफ यू वांट टू यूज दिस formula, first function x, for example, second function e power 3x. So first function as it is, integral of second function, minus integral of derivative of first function, integral of second function, and the product of the root 2 integrating. So e power 3x का integral e power 3x upon 3, x का derivative 1, e power 3x का integral e power 3x upon 3. Another integration has to be done. So x upon 3 e power 3x minus e power 3x का integral e power 3x upon 3. So 1 upon 3 becomes 1 upon 9, and problem solved. You can use this second approach also in any quiz or in any exam, but marks जब भी मिलेंगे जब सही लगाया होगा मेथड. और मैंने डेमोन्स्ट्रेट कर दी वही एग्जाम्पल यहाँ पे इस मेथड के जरिए. You follow it or not, it's your option. There is another method which is known as the tabular method of finding. Now the issue is that we have three kinds of problems when we are exposed to any exercise, exam on integration by parts. Some problems are directly solvable. And by directly solvable, I mean a problem of this type. No, this is not directly solvable. वो जो मैंने पहले problem discuss किया, this is directly solvable. Directly solvable का मतलब है एक दफा integration by parts लगाया और problem solvable. We can have problems in which we have to apply integration by parts repeatedly. And this is one of those examples. A simple example, x square e power x. First function x square as it is, इंटीग्रल ऑफ सेकंड फंक्शन माइनस इंटीग्रल फर्स्ट फंक्शन का डेरिवेटिव सेकंड फंक्शन का इंटीग्रल, and we are still up against an integration by part x into e power x. So ये वाला पार्ट जो है x स्क्वायर e power x तो इंटीग्रेट हो गया, -2 टाइम्स इंटीग्रल x e power x पर अभी इंटीग्रेशन बाय पार्ट दोबारा लगता है. So we apply the integration by parts on this. First function x as it is, e power x का इंटीग्रल माइनस इंटीग्रल ये टू कहाँ से आ गया? तो x का इंटीग्रल 1, e पावर x का x का डेरिवेटिव 1 और e पावर x का इंटीग्रल e पावर x. So we have got e power x here. This will be 2, not 4, because of this 2. तो इस प्रॉब्लम में इंटीग्रेशन बाय पार्ट्स 2 दफा लगा. So that is why I classify problems of integration by parts which are directly solvable. That means integration by part is only applied one time. Here, integration by part may be required to be applied many times. And there is another kind of problems where we have cyclic nature of integration by part. So where we have to apply integration by part multiple times, उसका एक particular case है जो यहाँ tabular method के तौर पर मैंने दिया हुआ है. I'll discuss that, but before I go for the discussion of that, okay, what are the what is the kind of problem where I use this tabular method? जब इन दोनों में से एक फंक्शन जो है वो पोलिनोमियल फंक्शन. अच्छा, तो हम क्या स्टेप्स इस्तेमाल करते हैं? पोलिनोमियल को रिपीटेडली डिफरेंशिएट करते हैं. याद रहे कि अगर आप एक पोलिनोमियल को डिफरेंशिएट कर रहे हैं, फॉर एग्जांपल आई कंसीडर px to be x square plus 3x plus 2. So what will be first derivative? The first derivative will become, ये second degree polynomial था, तो first degree polynomial आ जाएगा. Then you differentiate it again, it will become a constant. And ultimately, the third derivative of the polynomial will become 0. Second degree polynomial, third derivative 0. Third degree polynomial and fourth derivative will be 0. Tenth degree polynomial, 11th derivative will be 0. So फर्स्ट स्टेप इसके आप अपनी टेबल में पोलिनोमियल फंक्शन जो है उसको रिपीटेडली डिफरेंशिएट करें until the result is 0 and place these derivatives in a column. ये पोलिनोमियल फंक्शन फर्स्ट डेरिवेटिव, सेकंड डेरिवेटिव, थर्ड डेरिवेटिव until it becomes 0. पहले कॉलम में आपने पोलिनोमियल फंक्शन के डेरिवेटिव्स लिखे. सेकेंड स्टेप इज के जो दूसरा फंक्शन है, ये पहला फंक्शन जो था ये हमने p कर लिया था, इसके डेरिवेटिव्स पहले कॉलम में हमने लिख दिए. सेकेंड फंक्शन के साथ क्या करना है? सेकेंड फंक्शन को रिपीटेडली इंटीग्रेट करना है और जो रिजल्ट्स आ रहे हैं उनको सेकेंड कॉलम में डाल. सो ये सेकेंड कॉलम ओरिजिनल फंक्शन, first integral, second integral, third integral, and many times this integral will not vanish. लेकिन यहाँ पे पोलिनोमियल के जो डेरिवेटिव्स होंगे वो कहीं ना कहीं 0 आ जाए. So first column is filled with the derivatives of the polynomial. The second column is filled with the repeated integrals of the second function. And then we draw arrows connecting each entry in the first column to an entry in the second column, but in the next row. तो ये पोलिनोमियल और उसके डेरिवेटिव्स का कॉलम है, ये सेकंड फंक्शन उसके इंटीग्रल का कॉलम है. पहली एंट्री जो है पोलिनोमियल फंक्शन कॉलम की, उसको हमने कनेक्ट करना है फर्स्ट इंटीग्रल ऑफ द सेकंड फंक्शन. फर्स्ट डेरिवेटिव ऑफ पोलिनोमियल को हमने कनेक्ट करना है विद द सेकंड इंटीग्रल ऑफ द सेकंड फंक्शन. सेकंड डेरिवेटिव ऑफ पोलिनोमियल को कनेक्ट करना है थर्ड इंटीग्रल ऑफ द फर्स्ट फंक्शन. ये कहीं एक इंटीग्रल साइन कम लग रहा है मुझे. So there is first integral, second integral, third integral. There are three third integrals. Okay. So there is one additional thing. After this connection is built up throughout the table, we have to place labels plus or minus in each row between the two columns above each row. The middle column is for sign column. So starting with plus, plus, minus, plus, minus, plus, minus, so on. And then we have to combine the results to produce C. तो भाई हमारे पास जो रिजल्ट्स आएंगे वो Px will be linked with this. That means पहली टर्म ये आ जाएगी P prime Px related to this with a plus sign, P prime related to second integral with a negative sign, P double prime with a third integral with a positive sign, third derivative of the polynomial with the next integral with the negative sign. So alternate plus minus sign. Here is a demonstration of tabular method without making actually the table. We have the integral x cube sign. तो एक पोलिनोमियल है, एक सेकंड फंक्शन है. पोलिनोमियल के पोलिनोमियल x क्यूब, उसका डेरिवेटिव, उसका सेकंड डेरिवेटिव, उसका थर्ड डेरिवेटिव, फर्स्ट डेरिवेटिव स्क्वायर, सेकंड डेरिवेटिव दिस, थर्ड डेरिवेटिव and the fourth derivative. Fourth derivative is 0. Second function का इंटीग्रल, साइन का इंटीग्रल माइनस कॉस, साइन का सेकंड इंटीग्रल माइनस साइन, एंड सो ऑन एंड सो फोर्थ. तो हमने क्या करना है भाई, पोलिनोमियल को फर्स्ट इंटीग्रल ऑफ सेकंड फंक्शन के साथ मल्टीप्लाई करना है विद द पॉजिटिव साइन. पोलिनोमियल के फर्स्ट डेरिवेटिव को सेकंड फंक्शन के सेकंड इंटीग्रल के साथ मल्टीप्लाई करना है विद नेगेटिव साइन. नेक्स्ट टर्म and the second derivative of the polynomial is to be multiplied by the next integral of the second function with a positive sign. So positive sign, negative sign, positive sign, negative sign, so on, जब तक के हम derivative 0 तक नहीं पहुंचते. So this is a tabular method, but this tabular method is restricted to what situation? Where one of the two functions is polynomial function. One last issue before we can demonstrate more examples is in any arbitrary question, when we are given a problem, which function should be taken as first function and which can be taken as second function. So I start with an example. Integral x sine inverse x. Now, which function has to be first function and which has to be second function? So to make this choice, आप दोनों functions पर जरा अलग-अलग गौर करें. इसका डेरिवेटिव लिखना आसान है. The derivative is 1. इसका इंटीग्रल भी लिखना आसान है, x square upon. इसका डेरिवेटिव लिखना, here is the derivative, here is the integral. इसका derivative, I hope most of you know the derivative of sine inverse 1 upon 1 minus x square. But इसका integral लिखना itself a problem, because sine inverse x किसी function का directly derivative नहीं है, so इसका antiderivative लिखना मुश्किल है. So when we have to make the choice which is to be first function and which is to be second function, तो हमें देखना है कि अगर एक फंक्शन का मैं इंटीग्रल लिखना मेरे लिए मुश्किल है, I can't do this, so उसको मैं फर्स्ट फंक्शन बनाऊं क्योंकि उसका डेरिवेटिव लिखना मेरे लिए मुश्किल. So here the first function shall be chosen as sine inverse x, and second function is chosen as x, so that I write it as first function into second function. For clarity, I am putting the brackets. The pattern or the formula tells me that I have to start with the first function as it is. The first function as it is. Integral of second function minus integral first function ka derivative. So what's the derivative of first function? Is 1 upon 1 minus x square. And integral of second function derivative of first function, integral of second function, and then I proceed further to simplify this result. Sine inverse x into x square upon 2 integral of x minus integral 1 upon square root of 1 minus x square into integral of x, and that is x square upon 2 dx. And my result is still not complete, because the integration of this term is still required. X square upon square root of 1 minus x square dx. So what I have to do this with this integral, I have to solve it. So what technique should I be using to solve this integral? G. Any suggestion? There are only two people there, Ikra and okay, somebody said something. Substitution. Okay. Hamza said substitution. कौन सी substitution ये भी बता दो.
So 1 minus x square.
हाँ. 1 minus x square को क्या substitute कर? Just to remind you, थोड़ी देर पहले मैंने तुम लोगों को बताया कि कांस्टेंट माइनस एक्स स्क्वायर हो तो क्या सब्स्टिट्यूशन करनी. x is equal to sin theta या a sin theta. That makes dx, ये अभी थोड़ी देर पहले की बात है. So dx is equal to cos theta d theta, and the integral looks like x की जगह sin square theta, dx की जगह cos theta d theta upon under root 1 minus sin square theta. So sin square theta cos theta d theta, 1 minus sin square is cos square under the root becomes cos theta, and cos theta cancel. And I'm left with the integral sin square theta. Can I solve sin square theta? Whenever we are left with sin square theta, we use 1 minus cos 2 theta upon 2. Whenever we are left with cos square theta in any integral, we use 1 plus cos 2 theta upon 2, the elementary trigonometric formulas. I hope you people remember them. So this integral, जो कि इसकी जगह आया था, यानी integral sin square theta d theta, is now the form of 1 minus cos 2 theta upon 2 d theta, or 1 upon 2 integral 1 into 2 d theta minus integral cos 2 theta d theta. So 1 upon 2 theta, the result of this integration, minus 1 upon 2 cos theta. तो जब आप इंटीग्रेट करते हैं तो रिजल्ट आता है sin theta, but this is cos 2 theta, so it should be sin 2 theta upon 2. Now sin 2 theta, yes, we are at the stage where we have to look at the substitution that we made. We made a substitution, and view of that substitution हमें आगे बढ़ना होगा. Theta can be directly written down as sin inverse x minus 1 upon 2, rather it should be 4, sin 2 theta को हमें 2 sin theta cos theta के फॉर्म में लिखना चाहिए. इसलिए लिखना चाहिए कि sin theta will be directly x, this 2 cancel with this 4. Sin theta is written directly as x, whereas cos theta has to be written as 1 minus sin square theta. That makes the integral of sin square theta to be 1 by 2 sin inverse x minus 1 by, sorry, 1 by 2 into x root 1 minus sin square, and sin square means x square. So we have ultimately got the result for this. So this was our intermediate result. इस पूरे इंटीग्रल को सॉल्व करने के लिए हमें ये सारी कहानी करनी पड़ी. हमारा ओरिजिनल इंटीग्रल क्या था? Original integral was x sin inverse x. So result of x sin inverse x dx of इंटीग्रेशन बाय पार्ट्स हमने इस पर इस्तेमाल किया था, और हम ए पे पहुंचे थे जिसमें से वो पार्ट जो इंटीग्रेट हो चुका था वो एक्स स्क्वायर अपॉन 2 इंटू साइन इनवर्स एक्स था. जो पार्ट इंटीग्रेट नहीं हुआ था वो ये वाला पार्ट था, जिसके बाहर -1/2 था, और जो कुछ था इंटीग्रल उसका रिजल्ट निकल के आया है ये. So we place it here, 1/2 sin inverse x minus 1/2 x the square root 1 minus x square plus c. Now you can simplify this further, write down, but the result integration is complete. Now, have we lost the track of what we were doing? We were discussing the problem कि जब हमारे सामने product of two functions आए, so which function should be selected as first and which as second? So we discussed that कि जिस function का हम integral directly नहीं लिख सकते, उसको हम first function इसलिए इस्तेमाल करें कि उस फंक्शन का इंटीग्रल हमारे फॉर्मूले में नहीं आ रहा. हाँ, डेरिवेटिव आ जाए और डेरिवेटिव हम लिख सकते हैं. सो जिसका हमें डेरिवेटिव लिखना है अपने फॉर्मूले के अंदर, दैट शुड बी द फर्स्ट फंक्शन. भले से सेकंड फंक्शन का डायरेक्टली इंटीग्रल भी आता हो, डेरिवेटिव भी आता हो, लेकिन जिस फंक्शन का डेरिवेटिव तो आता हो लेकिन एंटी डेरिवेटिव या इंटीग्रल हमें डायरेक्टली नहीं आता है, तो उसको हमने फर्स्ट फंक्शन इस्तेमाल करना है. So first function is sin inverse, second function is x, first function as it is, integral of second function, derivative of first function, integral of second. So that was the actual purpose of the problem, but when we reached this form, we were stuck because this is required to be solved using the substitution. And I had already told you that whenever a square root of constant minus variable square हो, तो आपने x is equal to a sin theta substitute करना है. And more time was involved in this integration. पहले substitution के बाद जो result आया इंटीग्रेशन फॉर्म वो sin स्क्वायर आया. तो यहाँ मैंने आपको बताया कि अगर आपको sin स्क्वायर का इंटीग्रल करना है तो उसको इसमें चेंज करना है, cos स्क्वायर का इंटीग्रल करना है तो आपने इसको इसमें चेंज. Now that means what? In the demonstration of one of the situations, I came across a function which could be differentiated but could not be integrated. So I was forced to take this as a first function and then I have to solve it. लेकिन ये किस टाइप का प्रॉब्लम था? Out of these three, it was the first type, directly solvable, because only one integration by part is used here. Now, repeated integration by part का example मैंने discuss किया. We can discuss more problem of repeated integration by part. But I want to focus on cyclic integrals. So I consider another example to demonstrate a cyclic integral. E raised to power 2x into sine 3x. Now we know that हम e power 2x का डेरिवेटिव भी लिख सकते हैं और इंटीग्रल भी लिख सकते हैं. sin 3x का डेरिवेटिव भी लिख सकते हैं, इंटीग्रल भी लिख सकते हैं. So there is no preference कि कौन सा फंक्शन फर्स्ट हो और कौन सा सेकंड फंक्शन हो, लेकिन हम फॉर रीजंस इसका नाम रख देते हैं I. And then start solving it. जिस तरह से लिखा है मैं इसी तरह से फर्स्ट फंक्शन और सेकंड फंक्शन ले लेता हूँ. So जाहिर है कि we should remember that we are integrating product of two functions. First as it is, integral of second minus derivative of integral derivative of the first into integral of the second and then integrate again. So I start the process of integration by part. First function is e raised to power 2x as it is, integral sine 3x minus of the formula, integral of the formula, then the derivative of the first function. So e power 2x का derivative क्या है? 2 e raised to power 2x. तो मैंने डेरिवेटिव तो लिख दिया, अब मैंने इंटीग्रल लिखना है सेकंड फंक्शन का. So I'll go slowly, step by step. E power 2x. Integral of sine is minus cosine, but here sine 3x है, so minus cos 3x upon 3. Minus ये 2 बाहर आ गया constant. Integral e raised to power 2x. Integral of sine 3x minus cos 3x upon 3 dx. So what stage I am of solving this integral? Minus 1 by 3 e raised to power 2x cos 3x minus minus plus 2 by 3 integral e power 2x cos 3x dx. Now this is still a problem of integration by parts. That is product of two functions. So I keep all these terms as they are and focus on this integration by parts. First function, जिसको पहले first लिया था, उसी को अभी भी first लेना. E power 2x integral cos 3x dx minus integral derivative of the first function 2 e raised to power 2x into integral of the second function cos 3x dx. So I keep all these things as it is and focus on this part, e power 2x. The integral of cos is sine, but this is cos 3x, so the integral will be sine 3x upon 3 minus this constant 2 taken outside, e power 2x. Integral of cos is sine, but this is cos 3x, so sine 3x upon 3 dx. Let us look what we have right now. A part which is integrated minus 1 upon 3 e raised to power 2x cos 3x plus 2 by 3 into this term. That means e raised to power 2x sine 3x upon 3. 2 by 3 minus 2 by 3 into 2 by 3 ये वाला and integral e power 2x sine 3x. Oh, I have put 3 in the power. Sine 3x dx. And we see that this is exactly the same that we started with. That's a cyclic integration. So I finish the job like this. Minus 1 by 3 इन दोनों में 1 by 3 common है. Why not I take 1 by 3 common? Okay, why not 1 by 9 common? So it will become 3. There is something more common. इन दोनों में -1 by 9 जबरदस्ती कॉमन लिया मैंने, लेकिन e power 2x genuinely कॉमन है. What's left? Cos 3x, but यहाँ तो 1 by 3 था, so it should become 3 cos 3x. Negative taken common. 2 is not taken common. 1 upon 9 is taken common. Negative is taken common. So minus e power 2x is taken common. Minus 2 sine 3x. What about this? It is 4 by 9. And this is the integral that we started with, that is I. And we take this term to the other side. So when this term goes to the other side, it is 1i plus 4 by 9 I is equal to all this. I take 9 as LCM. 9i plus 4i, 13i is equal to all of this. That means I is equal to this 13 by 9 multiplied to this side minus 9 by 13 into 9 e power 2x 3 cos 3x minus 2 sin 3x. So 9 cancel out and we conclude I is basically e power 2x sin 3x dx is equal to, let us adjust for the sign, outside negative को inside ले जाएं. So result is e power 2x into 2 sin 3x minus 3 cos 3x divided by 13. Of course, there is a plus c. And I can generalize this formula to write down e power, this result, generalized as a formula, e power ax, constant a, sine dx, dx is equal to e raised to power ax. e की पावर में जो नंबर आया था 2 वो साइन का मल्टीपल है, सो a साइन dx. जो नंबर साइन के आर्गुमेंट में था वो यहाँ आया -3. I should not write down, मैं जनरलाइज कर रहा हूँ. b cos dx divided by what? 13. 13 is in fact 4 plus 9. 4 plus 9 is 2 square plus 3 square. इसका मतलब जो नंबर यहाँ आ रहे हैं उनके इसका स्क्वायर का सम a square plus b square plus c. तो साइक्लिक इंटीग्रल का एक तो फॉर्मूला बना. So that concludes in a way a discussion on these 3 types of problems that we face while solving exercises or exams or whatever, where we have to integrate the product of 2 functions. So I can focus on some of the very simple problems like x cubed minus 2x into sin x Another example. Now, what category this problem falls? Directly solvable, repeated integration by part, or cyclic integration by part? कैसे पता चलेगा मुझे किस कैटेगरी में आ रहा है? चलो भाई, कैटेगरी को छोड़ो, पहला फंक्शन कौन सा और सेकंड फंक्शन कौन सा? मैं इस फंक्शन यानी प्रोग्रामेबल फंक्शन का डेरिवेटिव लिख सकता हूँ और ट्रिग्नोमेट्रिक फंक्शन इसका भी इंटीग्रल लिख सकता हूँ और इसका भी इंटीग्रल, लेकिन आमतौर पे इस सिचुएशन में हम प्रोग्रामेबल फंक्शन को फर्स्ट फंक्शन लेते हैं। तो फर्स्ट फंक्शन एज इट इज, इंटीग्रल सेकंड फंक्शन माइनस इंटीग्रल डेरिवेटिव ऑफ फर्स्ट फंक्शन, integral of second function so x cubed minus 2x, integral of sine is minus cos, minus integral of sine is minus cos, so minus minus plus integral 3x square minus 2 cos x dx. So this tells me that I have to apply integration by parts again. So this problem falls into the second category, repeated integration. So I have minus x cubed minus 2x cos x plus first function as it is, second function integrate, मैं थोड़ा सा स्पीड अप हो रहा हूँ, sin x minus derivative of the first function 6x sin x dx. So now I have minus x cubed minus 2x cos x plus 3x square minus 2 sin x minus 6 times x sin x. So another by parts, and that makes minus 6 times x as it is, integral of sine minus cos minus derivative of x 1, integral of sine minus cos, and finally I reach the result x cubed minus 2x sin x is equal to minus x cubed minus 2x cos x plus 3x square minus 2 sin x minus minus plus 6x cos x minus minus plus minus minus integral cos x 6 times sin x plus c. This is our result. So one integration by part brings us to this second one. This second integration by parts brings us to this one. And then integration by parts is no more there, only an integral is there. But I discussed one point about problems in which one of the function is a polynomial. तो उसको tabular method से हम कैसे solve करेंगे? So this example is also an example of that situation. Px is what? X cubed -2x, इन बिटवीन मुझे साइन सेलेक्ट करना है और सेकंड फंक्शन gx इज sin x। टेबल बनाना शुरू कर भाई। फर्स्ट डेरिवेटिव 3x² - 2, फर्स्ट इंटीग्रल minus cos x, second derivative, this has to be connected with this with a positive sign. Second derivative is 6x. Second integral of sine is the integral of minus cos, that is minus sine. This one has to be connected with this or multiplied with this with a negative sign. Third derivative is 6. Third integral of sine is integral of minus sine, which is cos x. This has to be multiplied with this with a positive sign. Fourth derivative is 0. Fourth integral of sine is the integral of cos, and that is equal to sine. And this one has to be multiplied with this with a negative sign. Chunache, when we write down all these things together, this multiplied by this with a positive sign, this multiplied by this with a negative sign, so क्या बनता है? x³ - 2x plus minus of cos, sorry, प्लस तो यहाँ आएगा, ये तो मल्टीप्लाई हो रहा है, minus cos. Then next is negative. First derivative 3x² - 2 multiplied by second integral minus sin x plus x² derivative, that is 6x. 6x multiplied by this, then negative sign. Next derivative, oh, there is no next derivative. नहीं, एक टर्म बाकी है, नेगेटिव साइन, 6 into साइन. First term, second term, third term, and fourth term plus c. Compare it with this result. Isn't it same? This term, minus minus plus. इस टर्म में नेगेटिव साइन बिल्कुल सही आया, इस टर्म के अंदर कुछ पॉजिटिव नेगेटिव गड़बड़ हुई है, वो किस वजह से हुई है? ये माइनस माइनस, ये माइनस माइनस प्लस नहीं किया था. Now, if you have got the pattern in which this repeated integration is done, and you can afford going longer steps of integration by parts again and again, or if you have absorbed this tabular method of integration by parts, which is repeated, in which one function is polynomial. So ये method सिर्फ उस केस में लगेगा जब एक function polynomial, and the result will be the same. जिनको पैटर्न समझ में आ जाता है वो पैटर्न को इस टेबुलर मेथड जिनको समझ में आता है वो बहुत एंजॉय करते हैं टेबुलर मेथड को. So in exercise 7.2 you will find problems of all type, and by all type what do I mean is problems which are directly solvable, यानी उसमें इंटीग्रेशन बाय पार्ट एक ही दफा लगेगी, मगर हो सकता है बकिया हिस्सा उसका कॉम्प्लिकेटेड हो, जैसा कि हमने एक प्रॉब्लम किया था उसमें रिपीटेड इंटीग्रेशन बाय पार्ट्स, जैसे कि अभी हमने एक प्रॉब्लम किया, अगर रिपीटेड इंटीग्रेशन बाय पार्ट्स साइक्लिक में भी आता है, लेकिन अगर रिपीटेड इंटीग्रेशन बाय पार्ट्स इस्तेमाल हो रहा है, वहां पे जहाँ एक फंक्शन पॉलिनॉमियल है तो वहां टेबुलर मेथड भी इस्तेमाल किया जा सकता है. And then we have cyclic integration by parts, and there are many problems in which cyclic integration by parts. Yes. So that's it for today, and I will continue discussing some problems related to this today's lecture. That means the three types of integration by parts. And I'll select some of the problems from exercise 7.2, and I want to make an announcement that next week will be a quiz week on exercise 7.1 and 7.2, Wednesday and Thursday. Wednesday for one section, Thursday for the other section. So with that, I terminate today's discussion. If I will require any other extra session like I had on Friday and today, I will make the attendance mandatory, and from tomorrow onwards, I'll be taking attendance regularly. First, let me stop the recording.